In 1837, a mathematician in London sat down and designed a computer. Not a calculator, not an adding machine, a fully programmable, general-purpose computer, complete with a processor, a memory system, and the ability to run software stored on punch cards. The architecture was so complete, so correct, that when modern computer scientists finally analyzed the blueprints in detail, they confirmed every fundamental principle was sound. That machine was never built. Not in 1837, not in 1850, not in 1900, not in 1950. As of right now, with everything we know, with every tool available to modern engineering, the complete version of that machine, designed in the reign of Queen Victoria, still does not exist. This is not a story about failure. This is a story about a mind so far ahead of its world that the world never caught up. And it is not the only one. There are 6 machines from the Victorian-Era, designed, patented, in several cases physically demonstrated to work, that no one has ever successfully reproduced to their original specification. Not because the physics was wrong. In most cases, the physics was exactly right. But something about each of these machines sits in a gap between what Victorian genius could imagine and what any era, including ours, has been willing or able to complete. What you are about to hear is not speculation. Every institution mentioned is real. Every test result referenced is documented. Every claim comes from engineering records, patent archives, or the accounts of scientists whose names are still taught in universities today. Let's start at the beginning. In 1822, Charles Babbage walked into a room full of the most respected mathematicians in Britain and told them the era of human calculation was over. Mathematical tables, the enormous printed books that navigators, engineers, artillery officers, and bankers all relied on to perform complex calculations, were riddled with errors. Every table had been computed by human beings working in shifts, copying numbers, carrying digits, and making mistakes. Ships had run aground on those mistakes. Bridges had been miscalculated because of them. Babbage had found errors in 6 separate published tables in a single afternoon, and he was done. He had designed a machine, the difference engine, that would compute and print mathematical tables automatically, without a single human hand touching the numbers. The British government, recognizing this was not eccentricity but national infrastructure, funded it immediately. Over the following decade, they would invest £17,500 in Babbage's machine. The equivalent cost, at the time, of 22 brand new steam locomotives rolling out of Robert Stephenson's factory. What they got for that money was 1/7 of a machine, not because Babbage couldn't design it, not because the physics failed. The 1/7 that was built, 2,000 parts assembled by 1832, worked with a precision that stunned everyone who saw it. That fragment still exists in the Science Museum in London. It still works. Modern metrologists who have examined Joseph Clement's machined components have noted that the tolerances achieved were tighter than they had any reasonable right to expect from 1830s manufacturing. The machine stopped because Babbage and his chief machinist had a financial dispute. The government, burned by years of cost overruns and public ridicule from parliamentary critics who called the whole thing an expensive fantasy, walked away. The most important piece of precision engineering in the world at that moment was packed into storage crates, and Babbage went back to his drawing board. What he drew next was the machine that should have ended the Victorian era early. The analytical engine, conceived in 1834 and developed obsessively until Babbage's death in 1871, was not an improvement on the difference engine. It was a different category of object. Where the difference engine could calculate one class of mathematical problem, The analytical engine could run any calculation expressed as a program. It had a store, a mechanical memory capable of holding 1,000 numbers of 50 digits each. It had a mill, a central processing unit that performed arithmetic on those numbers. It accepted instructions from punched cards, drawing directly on the technology of the Jacquard loom. It could execute conditional branches. The machine could make decisions based on intermediate results and change what it did next. Every modern laptop in the world runs on these four concepts. Babbage had them all in 1837. Ada Lovelace, the mathematician and daughter of Lord Byron, grasped the implications more clearly than anyone. In 1843, she translated an Italian article on Babbage's engine and added her own notes, nearly triple the length of the original paper. In those notes, she wrote the first algorithm intended to be processed by a machine, a method for calculating Bernoulli numbers. She was the world's first programmer. Her program was for a computer that didn't physically exist, and still doesn't. The analytical engine required tens of thousands of precisely machined brass parts, operating in synchronization with tolerances measured in thousandths of an inch. Victorian metalworking could barely approach this. Friction alone, accumulating across thousands of interlocking components, would have seized the mechanism. Babbage knew this. Rather than build a simpler version to demonstrate the principle, he spent 4 decades redesigning, refining, and expanding the concept, leaving behind not one complete design, but a series of developmental drawings, plans, he called them, that capture a moving target, an engine perpetually in evolution. In 2010, British programmer John Graham Cumming launched Plan 28, a project to finally build the analytical engine from Babbage's drawings. By 2024, the project team had produced a 140,000-word technical analysis of Babbage's designs. They identified the most viable build targets. They assembled engineers, historians, and mechanical designers. They have not yet committed to breaking ground. The complexity of reverse engineering Babbage's intent from drawings that themselves were never finalized has proven, in the words of one project report, sobering. The most important computer ever designed has never been built. The man who designed it died in 1871 with a small experimental fragment sitting in his workshop. Surrounded by 40 years of drawings and the knowledge that he had been right about everything, except the one thing that mattered, whether the world would build it. 60 years after Babbage began drafting the analytical engine, a different kind of genius was working in a different kind of workshop on the island of Manhattan. It was 1898. The address was 48 East Houston Street, New York City. Police and ambulances converged on the neighborhood, convinced that an earthquake had struck. Walls were cracking. Heavy machinery was skidding across laboratory floors. People in the surrounding streets reported the ground itself was moving. There was no earthquake. There was a device the size of a toolbox, clamped to a steel structural girder, vibrating. Nikola Tesla picked up a sledgehammer and smashed it. The building would have been about our ears in another few minutes, he said later. Tesla's electromechanical oscillator had been patented in 1893. On paper, it was a straightforward steam-powered generator. High-pressure steam forced into a cylinder, driving a piston up and down, generating electricity through electromagnetic induction. The casing required pressures of 400 pounds per square inch and temperatures exceeding 200 degrees Celsius. Multiple versions used electromagnetic controls to lock the piston's frequency to a precise value. What made it extraordinary was not the electricity, it was the frequency. Every physical object has a natural resonant frequency, the rate at which it will vibrate most efficiently when external energy is applied at that precise rhythm. A wine glass shatters when a singer hits exactly the right note. Soldiers break step-crossing bridges precisely to avoid feeding resonant energy into the structure. Tesla understood this. More than understood it. He had spent years, by his own account, finding the exact dimensional ratios that allowed his oscillator to lock onto a structure's resonant frequency and feed energy into it continuously, amplifying the vibration with each pulse. Attached to that steel girder in Manhattan, his small device had begun feeding energy into the building's natural frequency. The vibration amplified. The structure began to respond. Tesla, watching his instruments, let it run until the last possible moment. He was, above everything else, a scientist. And then he destroyed the evidence with a hammer before the building could destroy itself. He claimed a sufficiently scaled version could be used to split the Earth in two. This was almost certainly theatrical exaggeration. But the underlying physics, mechanical resonance, amplification through precisely timed oscillation, is entirely real. It is the same principle that collapsed the Tacoma Narrows Bridge in 1940, when wind-driven oscillations matched the bridge's resonant frequency and tore it apart. Between 1896 and 1900, Tesla filed 8 separate oscillator patents. He gave lectures in which he described the resonance effects in detail. What he never wrote down, deliberately, to protect his patent position, were the specific dimensional ratios that produced them. He acknowledged in his own lectures that it had taken him years to arrive at the correct proportions, and that small deviations from those proportions produced nothing useful. Researchers and engineers have built mechanical oscillators in the century since. The basic steam-powered reciprocating mechanism is well understood. No one has reproduced the resonance effects Tesla described. The precise frequencies, the exact geometry of the resonant chambers, the operational parameters that turned a pocket-sized steam device into something that shook a city block. None of it is in the surviving records. The earthquake machine was smashed by its own inventor. What remains is 8 patents, a set of lecture notes with the critical numbers missing, and a police report from a Manhattan neighborhood that had no explanation for what had happened to it. On June 5, 1944, men in a room in Britain were staring at a piece of brass machinery that was about to make one of the most consequential calculations in the history of warfare. The Allied invasion of Nazi-occupied France was 48 hours away. Operation Overlord required landing over 150,000 troops on 5 beaches in Normandy under conditions of minimal darkness, low tide, and manageable surf. Get the tides wrong by even a few hours, and men would be landing in chest-deep water against fully visible obstacles, in daylight, with no cover. The planning teams needed tidal predictions for specific beaches, at specific hours, months in advance, with accuracy that left no margin for error. The machine they consulted had been designed in 1872 by William Thomson, who would later become Lord Kelvin, and refined by 1876 into a device that could compute 10 simultaneous tidal harmonics using nothing but rotating pulleys, a continuous wire, and a recording pen. It weighed approximately 2,500 pounds, stood 6 feet high, stretched 11 feet long, and operated by hand crank. It had no electricity. It performed no digital calculation. It was, by every modern definition, a mechanical analog computer, and it was more accurate for tidal prediction than anything else available. It helped plan D-Day. The landings were scheduled an hour, months in advance. The tides behaved as predicted. The machine's genius lay in Thomson's insight that tidal motion, the apparently chaotic rise and fall of ocean water, driven by the overlapping gravitational cycles of the moon, the sun, and dozens of smaller astronomical influences, could be decomposed into a finite set of pure harmonic oscillations. Each oscillation had a fixed period and amplitude for a given port. Add them together correctly, and you had the tide. Thomson built a machine that performed this addition physically, each tidal component represented by a rotating wheel driving a vertical displacement of the wire. All displacements summed mechanically, the result traced continuously by a pen. It was elegant to the point of being almost philosophical. The ocean's complexity resolved into interlocking gears. The problem was scale. 10 harmonic components gave good predictions for most ports. 30 components gave predictions accurate enough for military operations in tidal complexity. Every additional component required another set of precision-machined wheels and pulleys, each one calibrated to tolerances that accumulated error with every addition. Attempts to scale the Kelvin design beyond its original architecture ran into a fundamental mechanical limit. The wire that summed all displacements could only exert so much tension before the friction of additional pulleys overwhelmed the signal. Thomson himself identified this problem. He saw that his own machine would defeat itself if scaled. He had no solution. Kelvin was arguably the greatest physicist of the 19th century. The man who determined the correct value of absolute zero laid the thermodynamic groundwork for two of its fundamental laws and engineered the first successful transatlantic telegraph cable. If he couldn't see a path forward, there wasn't one using the materials available to him. The original Kelvin tide predictor served the British Empire for almost a century. When the Tokyo version was destroyed, it was not rebuilt. When digital computers arrived in the 1950s and 1960s, they simply replaced the brass machines entirely. Not by improving on the design, but by abandoning the mechanical medium altogether. No one ever built a tide predictor that exceeded the original Kelvin architecture while remaining true to its mechanical principles. The machine that planned D-Day is in the Science Museum in London. It is not in operation. Its performance has never been equalled in the same form. In February 1880, Alexander Graham Bell stood in his laboratory at 1325 L Street in Washington, D.C., and watched his assistant speak into a beam of sunlight. 200 meters away, through an open window, Charles Sumner Tainter held a receiver made of selenium, a light-sensitive metal, connected to a telephone earpiece. When Tainter spoke into the transmitter, his voice modulated a mirror that reflected concentrated sunlight toward the receiver. The varying intensity of the reflected light caused the selenium's electrical resistance to change in exact correspondence with the sound waves. The telephone earpiece reconstructed the voice from those electrical changes. Bell picked up the earpiece and heard a human voice transmitted through nothing but light. On June 3, 1880, the experiment was formalized. Bell's assistant transmitted a full wireless voice message from the roof of the Franklin School in Washington to Bell's laboratory window 213 meters away. It was the first wireless voice communication in history, predating radio by 16 years. Bell filed 4 patents on the Photophone. Of the 18 patents granted in Bell's name alone, these were the ones he ranked highest. He called the Photophone his greatest achievement, greater than the telephone, and he had invented the telephone. "The telephone communicates by electricity through a wire," he wrote. "The photophone communicates by light through air. The latter is the more revolutionary principle." He was right. The photophone was the direct ancestor of fiber optic communication and laser telephony, technologies that now carry the majority of all global data traffic. The concept Bell demonstrated in 1880 is the foundation of the modern Internet's physical layer. He was a century ahead of the infrastructure required to make it practical. That was precisely the problem. The Photophone worked with perfect reliability under one condition: clear line-of-sight transmission in good weather with strong sunlight. Rain scattered the beam. Fog attenuated it to nothing. Cloud cover reduced the signal below usability. Any obstacle between transmitter and receiver and the communication failed completely. The selenium cells Bell had access to were slow, inconsistent, and sensitive to temperature variation. The mirrors required constant manual adjustment to hold alignment. In a laboratory demonstration with ideal conditions, the device was flawless. In the field, in real weather, over real distances, with real operational requirements, it was unusable. Bell spent years trying to solve the atmospheric interference problem. He could not. The materials didn't exist yet. Coherent light sources that could punch through weather, lasers, wouldn't be invented for another 80 years. Low-loss transmission mediums that could carry modulated light across practical distances without atmospheric degradation, optical fibers, wouldn't become commercially viable until the 1970s. The British military independently tested the Photophone principle during World War I, attempting to establish wireless optical communication between ships in the Firth of Forth. The tests failed in operational conditions for precisely the reasons Bell had identified 30 years earlier. Bell's original 1880 device sits in the Smithsonian Institution. No working reproduction exists that matches its 213-meter transmission performance using the original selenium and mirror architecture. The concept was proven. The device functioned. What couldn't be reproduced was the world that would have made it practical, a world that arrived almost exactly 100 years too late. There is a version of history, not the one we were taught, but the one that lives just underneath it, in which none of this is coincidence. 6 machines, 6 inventors, 6 devices that were demonstrated to work, or were proven theoretically sound by the most rigorous minds of their time, or both. Not one successfully completed and reproduced to its original specification. Babbage died surrounded by 40 years of drawings for a computer the world wouldn't build. Tesla smashed his own earthquake device with a sledgehammer and took the key dimensions to his grave. Kelvin watched his tide predictor scale to obsolescence rather than solved. Bell filed patents on a machine a century ahead of its materials, and running underneath all of it, the same stubborn, recurring fact. The physics was right. The physics was always right. What stopped them was never the science. It was money. The British government's patience for Babbage exhausted by political embarrassment before the machine was half built. It was secrecy, Tesla protecting his patents by keeping the critical numbers out of his publications. It was materials, the atmosphere defeating Bell's light beams for 80 years, until lasers existed to defeat the atmosphere back. It was scale, Kelvin's elegant mechanism hitting a mechanical wall that only digital electronics could clear. The standard dismissal of stories like this is that we are seeing patterns where none exist, that these were simply hard engineering problems in a difficult era, that we romanticize failure when we should learn from it. There is truth in this. Not every unbuilt machine is a suppressed miracle. Not every inventor who ran out of money was ahead of his time. But here is what the dismissal cannot explain. Every one of these machines, when finally analyzed by engineers with modern knowledge, was found to be fundamentally correct. The difference engine was built in 1991 and worked on its first operational test. Computer scientists who analyzed the analytical engine blueprints confirmed the architecture was sound. Physicists who study Tesla's oscillator patents confirmed that mechanical resonance amplification at the frequencies he described is physically achievable. Optical engineers who study Bell's Photophone confirm that everything he built was functioning exactly as designed. These machines didn't fail. They failed by funding bodies who couldn't see the future, by the gap between one person's understanding and an institution's willingness to follow, by the brutal timing of being born at the exact intersection of imagination and impossibility. In 1832, that 1/7 of the difference engine sat in Babbage's drawing room. He would demonstrate it to visiting scientists, diplomats, dignitaries, and members of the royal family. They would watch it calculate and print a column of numbers without a human hand touching the result, and they would leave the room shaking their heads at the wonder of it, and then return to Parliament, or to their estates, or to their offices, and do nothing. The fragment of that machine is still in the Science Museum. You can see it. The gears are still aligned. The tolerances are still perfect. It still works. And somewhere in the same building, the tide predictor that calculated the hour of D-Day sits in a glass case, its pulleys idle, its recording pen dry. Two machines that changed the course of history. Neither of them are complete. Neither of them reproduced. Both of them waiting, in brass and steel and Victorian precision, for someone to finally ask the obvious question. What would we have become if we had finished them? Subscribe to this channel for more hidden stories like this one.